Yeah, so today I'm going to talk to you about the UAV geophysics workflow in Oasis Montage. And it's developed right now for magnetometer data. So we saw a lot of that today. And hopefully in the future, we'll do some workflows for EM drone data. But right now, the focus is magnetometer workflow. So just, Ron introduced me. I'm Laura Quigley. My background is geophysics, and I work with Sequent. So a bit of an agenda for today. I'm going to give a bit of background of who Sequent is for those of you who don't know Sequent. And what is our UAV Geophysics Extension? So a lot of the extension revolves around survey design, which is a big part of your drone surveys, as many of you know. And then it follows with data import, pre-processing, merging of that data, so often collected in sorties or sub-areas, and then followed by some timeline leveling. And then lastly, I'll look outside of our UAV geophysics extension and look at some other products you can generate with your magnetic data using some 1D and 2D filtering extensions in Oasis Montage as well. So who are we? So Sequent brings together industry-leading Earth modeling, geodata management, and team collaboration software. So here's a few of the products. A lot of you might know Leapfrog in the mining space and other spaces as well, environmental and civil. Geosoft, so we have a lot of different extensions. Let's check. There we go. So Oasis Montage, I'll be focusing on today, our UAV extension. We are also our house Geosoftware now, so we have Workbench, Imago, GeoStudio for civil applications. So a whole range of products. And today, like I said, I'll focus on Oasis Montage. So our UAV geophysics extension was built to streamline your magnetic airborne UAV survey, complete workflow from beginning to end, which includes planning your survey based on the range of your drone, so the time it can fly. And also we take into account the visual line of sight of your drone throughout the whole survey. Importing and processing the data, of course, and then correcting that, leveling that, merging that seamlessly into one grid. Okay, so now I'm going to switch over to Oasis Montage and hopefully show you what that looks like. I might sit down a little bit because yeah, so I didn't introduce the data yet. So I'm going to be looking at a data set from the Crestone Crater that was generously given to us by Ron Bell. This survey was flown in 2019 over this crater here, which is about 100 meters across. It was flown with the drone, the Mag Arrow in the Great Sand Dunes National Park. So on the screen here, I have the DEM. So you can see the berm of the crater nicely here, and also this survey polygon. So it's just an outline of where I want to fly my drone survey. So this is Oasis Montage, and this is basically the first, or the two main things you need to plan your UAV survey. So across the top, we have our main menus, and then the UAV extension is here. So I'll focus mainly on this workflow. So really, you just start with the survey planning and it ends with intersection leveling. So it's a linear workflow to help you plan your survey. So survey planning involves, of course, the first step would be to plan your survey. So that involves giving it a survey name, the survey polygon, which you saw in white, a digital elevation grid, and then you can design your terrain clearance. So here I have 1 meter for my drone to fly above the terrain, 10-meter line spacing. We can also add a waypoint. In here, I've decided to add tie lines to my survey. So this is, I'm going to put those at 50-meter line spacing. And that's all we really need to plan the survey. So if I click OK here, it's going to generate a flight path for me in Oasis Montage. So the program will do that. Let's hit cancel and show you what that looks like. Okay, so just by creating that plan survey, you have your flight plan here. So the next logical step would be to break this up into sorties or sub areas. So as we all know, drones have a limited range of flying time. So we can run the define sorties sub area tool. And here you just enter the name of your survey, which I've called Crestone Crater. And then we can choose to calculate the sortie based on a nominal, this will change to a nominal distance. So it could be 2,000 meters before you need to return and recharge your drone. Or if you have survey polygons already drawn, you can use the import survey polygon. So here I've broken up this area into 2 flights. So that is here. Let's turn this one on. And I'll turn off the path for now. Okay, so here we have defined 2 sorties in green and in red. The program will also give you the best, or what it thinks to be the best takeoff location for each sortie. So these white dots here on the screen. Essentially, that is at the highest elevation of each sortie. If you don't like that location, we do have a tool to then go in and move your takeoff locations. I do have internet, but I will, I'll try and bring up, in Oasis Montage, you can add Azure Map Imagery from our data services, so outside the UAV extension. So this comes with the core Oasis Montage. We can add Azure Map Imagery. So if you need to know where there's an accessible road or a parking lot or something you can easily take off from, you can use Azure Maps. It can be a bit slow to render if the internet's not great, or if you don't have internet, you obviously won't have access to this. So then you can come in here and say, oh, there's a road down here. Maybe I'll move my takeoff location from here to here. And this is all part of the survey planning still. Okay, so the next step after we have defined our sortie polygons and examined the takeoff locations, we want to define a survey path for each of those sorties for the pilot. So we just run the define sortie path tool, extend a little bit outside the plan lines, to allow for turnarounds. Okay, and then we end up with, I just have one path drawn here. I'll turn off the DEM. And we also give directional information. So we now have this planned path for sortie 1. And these arrows just define the direction, the takeoff location is still here. And so this is your planned survey path. Okay, so we're almost done the planning stage, but an important step after you define your path for both your sorties or multiple sorties that you have, you'll have everything I'm showing here, by the way, on the map is also in a database. So we have what we call a path database for each sortie once we define that path. So it's those XY coordinates. Then you'd want to test the line of sight. So a lot of the talks today talked about how important this is. So we have a tool in the UAV workflow that'll do that for you. You generate a map, which I've just called visual line of sight, sub-area 1. You tell the program the terrain clearance of the drone, 1 meter, and the takeoff height. So for me, I just put in 1 meter. If you're on a ladder or something, at a crane or something, you could put in that respective height there. And that's it. So the program, this takes a little bit of time to calculate, and the end result is this map here, which where we display where you can and can't see your drone, just based off basically the drone height and the observer, and the DEM and the pilot's height. So everywhere in white is where you can see the drone. And these colors indicate the depth below line of sight. So anywhere from 0 to 6 meters below the line of sight. So that's good. You can go in and readjust. You might need to add an observer. You might need to move the pilot. You might need to increase your takeoff location. So we have that option here. So you just go back into test line of sight and maybe add an observer. So this is just a text file with the coordinates, and you would have to activate that and give the observer height. and then run the tool again and see, okay, if I add somebody to my survey in this, say, bottom left corner, am I now able to see the drone at all times based on the digital elevation? Now that'd be 2 people and the flying height, whatever you choose. Okay, so then you're almost, once you have all that figured out, you're ready to fly. You have a survey path, you have hopefully your line of sight sorted out, and then you can export that to a KML file and give that to the drone pilot to fly. So you go out and you fly your survey, and the next important thing you'd want to do is import your data and start the processing. So in the UAV extension, we have the option to do import sortie, just a single sortie, or do a batch import. So if you fly multiple days of data and you want to do all your processing at once, we can do a batch import. So I just want to show you I'll just turn off the plan here, and I'll show you the imported data. So these are the flight lines that have been imported from the 2 flights that were flown over the crater. So you see, we have turnarounds, we have the ferry to and from the survey block. So we haven't cleaned this up yet, but this is the raw flight path. And right away, you can actually start gridding up your data. So I've gridded the magnetics data from the mag arrow here, which looks okay, even in its rawest form. You can see there's merging issues and leveling issues. And of course, we need to clean up some of the ferry to and from, and just keep the data we want to analyze and interpret. So that's the raw data. And then the next logical step in the workflow would be to pre-process your data. So we have a host of processing tools here. So remove data discontinuities is a big one. So often if there's dropouts in the mag arrow, I think fairly common, or spikes in your data, this will spline through them. You can apply your base station corrections here. So you just upload your base station file and that is applied here. If you needed to apply a lag correction, that can be done in the pre-processing as well. And heading corrections. So often if the mag arrow is flying in one direction versus another, there will be a slight difference in the magnetic reading. So if you do a heading test, I don't know if anyone's talked about that, but if you do a heading test to get that slight offset of directional dependence of your mag arrow, we can apply that heading correction here as well. So then the final step, or not the final step, but you're almost there. You want to merge your processed sorties together. So in the UAV workflow, it's a 3-step process, but you essentially just walk the program through. So you look at each sortie database and identify which survey line it lines up to. You split that database into its respective lines, and then we do some merging of that data, averaging to seamlessly merge your sorties together. So I'll just show you that merged data. So just turn this one. Okay, so this is what your final grid of your magnetics after the spikes have been removed, all the pre-processing turnarounds have been cut out. When you do the splitting on the lines prior to merging. And it looks pretty good. We still have some leveling issues. However, tie lines were flown with this survey, so we can do some tie line leveling, which is also built into the workflow. So here we will add our tie lines to our merged database. And I'll just open that up to show you because I've just shown you really the maps, but this is our data in database form. So we have a mag channel here displayed in profile view. I have my digital elevation displayed here. So all this data that I've shown you in grids and maps is all here. You have your lines listed here, so you can click through them. We have our tie lines in this database as well, so we're ready to do some intersection leveling. Okay. So once we run this tool, we have the leveled, it's a simple tie line leveling, and we get a grid that's a little bit more leveled. So a bit better for interpretation, and that corrugated, not really real magnetic signature is gone. So that's kind of the UAV geophysics workflow. So from survey planning right through to your pre-processing and your intersection leveling. Oftentimes you want to provide additional products, maybe first vertical derivative or analytical signal. So we have extensions for that as well in Oasis Montage that I've added here. So we have our 1D filtering and our 2D filtering. So 2D filtering will act on filter your grids for you. So in our 2D filtering, if you want to apply the first vertical derivative, so I've just set that up here as an example. So I input my leveled grid and we can edit the filter here. So it's pretty interactive. You can choose a list of filters here, derivatives, bandpass filters, reduction to pole, and your inputs on the top, and you can preview the output here on the bottom. So this is a really great way to produce those additional interpretation products that you might require. So I'll just cancel that and show you those grids. So here I have, this is the first vertical derivative. So great for showing the outline of the crater, any kind of shorter wavelength features that you want to enhance. And as well, we can also calculate the analytical signal. I've also applied a bit of smoothing to these grids. So there's various things you can do to make those additional data products. And if you want to take your data a step further and go into 3D, you can do some inversion of your surface magnetic data using our Voxy extension. So in Voxy, we can invert your magnetic data and give you a 3D voxel or a 3D cube, which will start to show you a bit more about what's happening at depth with this crater, for example. I believe actually the origin of the crater, as Ron said, is not really known. So it was hypothesized to be an impact crater, but later geologists found that this might not be the case. So I think maybe looking at it in 3D will start to help tell the story about how this crater came to be. I haven't really looked too far into it, but I can show you what the data looks like in 3D. So in Voxy, you can do a magnetic susceptibility inversion, or you can do the more advanced MVI, which is a magnetic vector inversion. So that's when we're counting for magnetization in the rocks. That's not only from the induced field, but from remnant magnetization. So I do have a slide on that. I'm not going to get too heavily into the math, but we do MVI inversion. So not just your traditional susceptibility. And that does result, you'll get your 3D model of the subsurface, your amplitude, your magnetization amplitude, but you'll also get the vector voxel. So basically just a bit of physics, like if you're doing your susceptibility inversion, we assume that all the magnetization in your rock is in the direction of the inducing field, which isn't often the case. So if there's remnant magnetization in the rock, for example, we're going to have vectors that aren't in the inducing direction. And we do want to solve for the magnetization, as this is a natural parameter for describing the magnetization of the rocks. So we do want to take into account that anisotropy. So why do we need to consider MVI? A significant percent of magnetic inversions yield geologically inconsistent models. And the conventional susceptibility does fail to account for that remnant magnetism, like I said. And research is suggesting the importance of including remnant magnetization in your inversions. This is an example, not in Greystone Crater, but I thought it was one cool example I found. So you have a rock here and the Earth's magnetic field. Conventional susceptibility inversions assume the rock is magnetized in the direction of the field. The target here is this white mineralized zone here. And with the conventional susceptibility, we don't really pinpoint that target quite accurately. You know, you have these lobes off to the side of your magnetization. If you do the MVI inversion, you get that much cleaner pinpointing of that anomaly here. And that's due to a lot of this has remnant magnetization in it. Okay, so that's a little bit off, just a little bit more about our MVI inversion. I've run one in Oasis, so I'll quickly show you what that looks like, the 3D cube. So I've run a conventional susceptibility inversion, but I think, you know, if you have the option, why wouldn't you run an MVI? So here's our crater in, or our Keystone crater area in 3D. You can see the outline of the crater. You get a couple of voxels out of that inversion where it is the MVI. So I have the amplitude here. The E perp is the component of the magnetic field perpendicular to the induced field that we've returned. And the E proj is another component of the magnetic field. This is the component that's in line with the Earth's magnetic field. So we do see a lot of induced magnetization in this particular area. So the susceptibility inversion doesn't look too much different at first glance. So we have our amplitude here. We also get these vectors back, and you can start to clip those, basically directional clipping for vectors to see vectors that are in line with your IGRF field here, about 65. So we do have a significant portion of vectors that are lining up with the induced field. So that's just a bit about VOXY and the capabilities of the MVI inversion. So we can take depth slices through the voxel. So here I've just grabbed one at 10, 50, and 100, I believe, to show. So yeah, just turn those off and start. Yeah, at the surface you can, oh, that one's at 40. So no, this is the surface. At the surface, you can see that nice outline of the crater. And if I go down a bit deeper, say down to 40 meters below ground surface, you can see the outline is less apparent and it's more homogeneous. So you're getting, you're kind of losing that crater maybe by about 40 meters depth, and you're just getting high magnetization maybe from other rocks much deeper, but you're losing that crater. And then just taking a slice down at 100, you'll see some strong signal, but yeah, you don't really see that crater anymore. And then I've taken just a quick cross-section in the cross-section view, so just right through the crater. And you can kind of see, I know that the berm of the crater has magnetic soils, so that's what we're picking up here and here. Yeah, I have the arrows turned on, but they aren't necessary at the moment. So you can potentially see that these magnetic soils extend down to about 50 meters maybe. I don't know, is that an impact crater? So that you can start to use these products to hypothesize about the origin. I don't see any other geology standing out here that came through in the inversion, that would tell me much more other than kind of the depth of those soils. Those magnetic soils that were surrounding the crater. Yeah, and let's jump back over here. So that was our UAV workflow and our additional products such as 1D and 2D filtering, and as well as the voxel 3D inversions. Yeah, and so hopefully if you have any questions, you can reach out to me, and if you find this useful for UAV magnetic surveying. Thank you.
Wow, thanks a lot. That was a really great talk. Really interesting software. So I'll bite. What is it? If it's not an impact crater.
No, it's not. I believe what it is essentially a sand boil, where
Which
you have
is?
there was a
Which is?
well, you had a seismic or some event that caused the water pressure, the hydraulic head, to be energized, and it pushed out water off the surface like a geyser, and it brought up coarser grained material that set on the surface in a circular pattern, and then the sands that are on top are about 4% magnetite. So what we think is happening is that the infill between the sands infill between these coarser grained rocks that got pushed out by this sand boil.
But it goes deep though. It goes down.
No, it doesn't. And she actually showed it from the modeling, is that it actually has a very much a bottom.
40 meters though.
Yeah,
That's
about 40.
pretty deep, but it's still.
Okay.
It's
I'm no
limited.
geomorphologist. Yeah. Don't we have a quaternary geologist in the crowd?
Well, it's actually subject to a lot of discussion.
Okay.
What's the cause of that?
Well, we're getting off track.
Yeah.
Anybody got any questions on this?
Well,
on
I
this
would like
UAV?
to point out one thing. Lori just said there was the mag arrow you used, and that oftentimes you get dropouts.
Dropouts, yeah.
And that doesn't really happen with mag arrow data. It is
Okay.
dropout free. So I
Oh.
just wanted to correct you
No,
on
that,
that. So,
okay, yeah, I have some, we have drone mag, we have mag arrow, so,
yeah, I won't talk about the drone mag because I've never seen any of that data.
okay,
But the mag arrow itself has two sensors in it that are orthogonally oriented. And that means that you don't, there are CCM sensors, you don't have any dropout.
okay. That tool can also be used if you get spikes in your data. I don't know if that happens often either with mag. It's essentially just to get rid of those high amplitude, most
Well,
often dropouts, but maybe not with a mag arrow.
With the oil wells, you get pretty high.
Yeah, you
amplitude.
went over an oil well. That's what
Yeah.
happened.
Yeah, but you
This
don't want
is not an
those
oil well.
to be filtered out. Yeah,
I would just say that I don't know, did you desample that data or filter?
I
it?
didn't desample this one, no.
Okay, that's pretty clean data. Very often, at least in the States, you get a lot of 60 hertz noise in the data because we're sampling at 1,000 hertz. And it's just a fact of life. It's pretty low amplitude stuff, but I use it as actually, I think that there's probably some near surface geologic information in it. And I haven't sorted out what it would be yet, but it's really basically if you have a power line and it's putting 60 hertz signal into the ground, it's actually creating currents to flow, and there could be some geologic information to be extracted from it.
Okay. Oh, we got a question. Doug. You got a soft voice.
Yeah. Thanks very much. I just had a question. When you were setting the survey up, you put the height of the drone at 1 meter, and then so was that actually how the survey was carried out? Was this was this drone data, and B, was it acquired at 1 meter height?
Yeah, no, I think it was acquired at 20 meters height. I was just showing that for planning purposes and also to get a reaction from my line of sight tool to say that, oh, I can't see. If it was up higher, we would have had a plain white map because you could see it everywhere. Yeah.
Good answer.
I'd like to actually add to that. We flew it at 20 meters because we were mapping geology. And I knew that I was going to get a response over the Crestone crater because I'd already mapped it several times. But what you pointed out is that when you fly at 1 meter or ultra low altitude, there are times you can't see the aircraft because of the just small variations from in the topography can actually, and this happens to us on our landfill test site. It looks flat, but it isn't. It gets away from us probably several hundred meters away, and it's below the horizon. So that planning tool is pretty effective. I hadn't used it for that reason before, but it's a nice thing, particularly if you're flying ultra low altitude surveys.